We're going to continue talking about solutions today, specifically the colligative properties. Yesterday we talked about calculating the boiling point of the solution. We know the boiling point gets elevated when solute is added to solvent. Today we're going to talk about freezing point depression. We're going to be calculating the freezing point of a solution. When you add solute to solvent, the freezing point of the solution gets depressed or lowered. This is one of the reasons why they salt roadways up north when it snows. You will see that the freezing point of the solution, the salt water, is less than the freezing point of the water alone. So it has to get even colder in order for the roadways to freeze. And if you've ever been up north during a snowstorm, it's very hazardous driving conditions, and driving on ice is a very big challenge. Up north, when we took driver's ed, we already had our licenses, so they actually allowed us to learn things that we probably hadn't seen previously on the road. So one of the things that we did in driver's ed, and keep in mind driver's ed was Saturday morning. It wasn't a class that you could take in school or online. We didn't have online learning way back when. So you would basically go to sleep in sweats, and you'd roll out of bed in the morning, and you'd have to be there at 7 a.m. on a Saturday. And so people usually looked pretty amusing, a little bit of hat head and everything else. So in any event, one of the things we did is we used to drive out back on a pond. So they'd push the car, or you would drive onto a sheet of ice, and you would have to try and drive very slowly and get off the sheet of ice. And it was really fun and very challenging and not something easy to do. One thing you did learn, and this is something that would be useful down here as many of you are starting to drive, is you always drive into a skid, not out of a skid. And your gut reaction is to drive out of it. But with practice, you learn how to do that.
Is that safe driving on a pond?
Well, we had a driving instructor with us, so it was all good. It was a lot safer than when I went ice skating with my daddy and we fell through the ice. I'll tell you that story afterward, but about 6 people came out to rescue him, but they just said that I could crawl out and keep going. I was about 5. Oh, it wasn't like a big pond. It's just like a sheet of ice. It's all good. It was fun. It's good learning. In any event, when you add solute to solvent, the freezing point of the solution gets depressed. Down here, what would be more relevant is, for example, if you were dealing with crops, keep in mind that oranges don't only contain water, they contain sugar. And so the orange is not going to freeze at 32 degrees Fahrenheit. It's going to have to dip below 32 before the oranges freeze and the crop is potentially ruined. So today we're going to focus on freezing point depression. Next time we'll get into molar mass determination from colligative property data. But today, freezing point depression. So I already showed you the formulas that are involved in freezing point depression, but I again want to illustrate that if you had a beaker of water, water has a freezing point of 0 degrees Celsius. And we know water has a bent molecular geometry. We talked about the fact yesterday, or reminded you of the fact that water molecules link to one another through intermolecular forces, London dispersion forces, dipole-to-dipole interactions, and shown here is a hydrogen bond. For water to freeze, those intermolecular forces must be able to form, and form in a particular configuration. There's a hexagonal array, and I've shown you that before in regard to melting, so here we're just building it up. So you have a complete network of water molecules when water freezes at 0 degrees Celsius. If you throw solute in to the water, let's say sodium chloride or any salt, that solute acts almost as a traffic jam, preventing the intermolecular forces from fully forming at 0 degrees Celsius. And now the temperature has to be even lower for the solution to freeze. So the freezing point of a solution is less than the freezing point of the solvent. And as we saw in the do now, there will be two formulas that you will use. Delta TF is equal to KF times the molality times I. The KF is the only new piece. I'll point that out in a sec. Once you calculate your delta TF to get your freezing point of your solution, you are going to subtract that delta TF that you calculated here from the freezing point of the solvent. So that's the key difference here. And if you remember freezing point depression, you will remember to subtract the change in freezing point from the freezing point of the solvent. So these are the two formulas we're going to use. We'll have two new constants, and you can see those constants on the back of your periodic table in Table 2, which is shown on the screen. We're going to be focusing on these last two columns. You need the gold periodic table or your second semester periodic table that I provided you with earlier this 9 weeks. The solvents shown here as we saw yesterday, for example, benzene, a nonpolar covalent solvent, freezes at 5.533 degrees Celsius. Its KF is 5.12 degrees Celsius per molal. Phenol freezes at 40.90 degrees Celsius. Its KF is 7.40 degrees Celsius per molal. So today we're going to be using these last two columns here for freezing point of the solvent and the molal freezing point constant. Other than that, you're going to work through these problems grossly similar to what we did yesterday. Let's take a look at these two examples. We'll work the first one together, and we'll see if you can work the second one on your own. It says, at what temperature will sodium chromate solution freeze? That's what we're looking for. We have 103 grams of sodium chromate dissolved in 800 grams of water. So let's get that down and let's figure out how to process this. I think you'll find this to be very straightforward after having worked through some problems yesterday with boiling point elevation. So here we want to know the freezing point of the solution. As soon as you see freezing point, remember it gets depressed. It's got to be less than the freezing point of the solvent. The mass of the solute is equal to 103 grams of sodium chromate the mass of the solvent is 800 grams of water. We know that delta TF is equal to KF times the molality times I. What should we do? What's our solvent? Water. So I'm going to look at water. What's our KF for water? 1.853 degrees Celsius. I'm going to do it per molal. I think you'll find it to be easier. How do we get our molality? We need to get moles. So we're going to get moles of solute. And then do we just plug that in here? You better not. What are you going to divide it by? In kilograms, right? Move the decimal 3 to the left. So 0.636 divided by 0.8 is 0.795 molal. If you're not comfortable doing this, you can do like this. That'd be the unit for KF, and you can use the unit for molality and cancel left there. Or you can just do as I did here and cancel the mole out, if you will. Whatever's easier for you, same result. The other thing we need to do is we need to get I. Do we use the solute or the solvent to get I? That will be the solute. So we grab our solute, we show our dissolution reaction or dissociation. We've got sodium ion, group 1, 1 plus, chromate ion, 2 minus, balance for charge, balance for atom. What's your I equal to? 3. And I'll need to see this equation to get full credit for this. And our delta TF is 4.42 degrees Celsius. And what do I do after I get my delta TF? I must subtract it from the freezing point of the solvent. It is okay to get a negative temperature for the freezing point of solution, especially if your solvent is water. That's all you will get. So this salt solution freezes at negative 4.42 degrees Celsius, and if you sprinkled this on the roadways, which you would not, now it has to be even colder out for the roadways to freeze, so you're not driving on a little pond. Pretty straightforward? All right, next one together or on your own? Together.
On your own.
Whatever you want. Here, I'll help you pull the stuff out and then you give it a rip. On number 2, it says, at what temperature will a barium acetate solution freeze? That's what we're looking for. You have 84.5 grams of barium acetate dissolved in 788 grams of phenol. So let's get that down and let's see if you can get it to rip. We want to know the freezing point of the solution. The mass of the solute is 84.5 grams of barium acetate. Acetate, you know, all acetate ion containing substances are water soluble, so they're commonly used. Be careful when you add up the pieces for the acetate in there. It might be easier to do that way, as we've talked about previously. What's the mass of the solvent? 788 grams, and your solvent's phenol. Make sure you note the solvent. You're going to need it for table 2. There are your pieces. This problem should take you maybe 4 or 5 minutes to solve. Give it a try. How we doing? All right, when you're done, you'll look up to check your answer. Don't peek until you've got it. You have an answer? Alrighty. Now, if you've peeked and you didn't match my answer, really look at my work and see where you might have gone awry. Did you have the right formula mass? Did you have the right moles? Did you have the right molality? Did you have the correct I determination with the work shown? Did you have the correct delta TF? Did you remember to subtract? Did you use the right freezing point for phenol? How'd you do with it? Pretty good? And these problems really just require, you want me to go a little bit larger? Sort of hangs off at the end if I go too big. And these really just require some practice. And as I said yesterday, classwork 3.3, numbers 15 through 16 require you to calculate both the boiling point, you did some of those yesterday, and now the freezing point. And if you were organized in your classwork, you already have the M and the I. And so now you can go after the freezing point. Remember, the freezing point gets depressed when solute is added to solvent. The boiling point gets elevated. Boiling point elevation and freezing point depression are just two colligative properties. There are more. It's not something we really require that much of at the honors level. I like you to see the freezing point depression and the boiling point elevation. Unfortunately, they've both been cut from the AP curriculum, which I think is a shame. But some of you are going to take SAT 2 next year, and just a few things here will help you along. I do want to mention that other colligative properties include osmotic pressure, and this is the pressure that tries to prevent osmosis, as well as vapor pressure depression. For those of you who are interested, I'd be more than happy to show you how to work these problems. There are some problems on your classwork, but you won't be assessed on them. I will not assess on that in any regard. And what we're going to get into next time is determining molar or molecular mass of the solute from freezing point of solution or boiling point of solution. So we're basically going to be working everything backward to determine the molar mass of the solute. So this is what we'll be getting into next time. That'll be the last lesson. These are just two other colligative properties. For those of you who want to give it a shot, I'd be happy to show it to you. Osmotic pressure is assessed in AP Bio, so if you're moving in that direction next year, it might be a good jump start for you, and I'd be happy to show that to you. So what you really want to make sure is that for tomorrow you've got your classwork done so that you feel confident with this concept. It's not difficult, but there are many steps. And if you get practice with it, you will be very successful with calculating both freezing point of a solution and the boiling point.